All right, so I'd like to give an overview of the project that we're doing in this first unit of physics. And the essential question for the project is, what is this stuff? What is the stuff in this bag? So in this bag, there is a clay-like substance. Yes, it looks like Play-Doh, but it could be some other kind of clay. Substance has clay-like properties on it. You are going to tell me what kind of clay it is. It could be Play-Doh, it could be air-dry clay, it could be the kind of clay you can make at home in your kitchen, it could be the kind of clay that an artist uses when they're making ceramic pots. You're going to tell me that. So the essential question is, what is it? That's the essential question. Now the way you're going to be able to find out, this is like you're being an investigator. This is CSI. You're going to go to the lab and you're going to perform some experiments and you're going to do an analysis of this material. One of the ways to do that is to find the density of your unknown substance. Find, or let's say measure. You're going to measure the density in the lab, and then you're going to compare that with the density of other known substances. And if you measure a density and then you find on the internet some material that has that exact same density, then there's a good chance that this is that material. Right? So what is this density? Density is equal to the mass over the volume. How much matter is here and how much space does it take up? I call this the broken-hearted unit because it's mass over volume, and that kind of looks like a broken heart right there. All right? You're going to measure the density indirectly, because I don't have a densitometer. But I do have a scale that you can use to measure the mass, and I do have a graduated cylinder that you can use to measure the volume. Okay? So your first task is to measure the mass and then to measure the volume of the material. Inside the bag are 4 different sized balls. You could call them tiny, small, medium, large balls. Tiny, small, medium, and large. Okay? I want you to make a data table where you list the mass and the volume for each of these balls. So let's just say you get the triple beam balance scale and you weigh the tiny ball and you get, let's just say, 5 grams. And then you weigh the small ball and you get 7 grams. Okay. And then you weigh the medium-sized ball and you get 10 grams. And then you measure the large ball and you get 15 grams. I don't know how much these balls weigh. That's what you're going to find out. And it may be different for every student, but you're going to use your sample. Then let's say you measure the volume and you get 10 milliliters of the tiny one. And then maybe you get 14 milliliters for the small one. And then maybe you get 20 milliliters for the medium-sized ball, and then 30 milliliters for the large ball. This is what I'm looking for. I'm looking for you to collect the data for the mass and the volume for each of the balls. Then I want you to graph this data. Okay? You can make a graph. I didn't leave myself a lot of room here. Let's see. I have to kind of scrunch it up. I want you to put mass on this axis and I want you to put volume on this axis. The reason I want you to put mass here and volume here is because mass over volume here, you're going to need when you measure the slope of the line of best fit for your data. Okay, I went really fast. Let me back up a second. The first thing to do is to make a scatter plot of this data. So let's see, if this was 5, 10, 15, 20, 5, 10, 15, 20, 25, 30. Okay. First data point, 5 grams, 10 milliliters. 5 grams, 10 milliliters. Second point, 7 grams, 14 milliliters. 7 grams, 14 milliliters. 10 grams, 20 milliliters. And finally, 15 grams, 30 milliliters. So you'll get a scatter plot of your data, and then you're going to draw a line of best fit. By a line of best fit, that doesn't mean that it goes through every point, but it should come as close as possible to each point. Okay? So maybe it misses a couple. You get to be the judge of where that line goes. The slope of this line, is equal to the rise over the run, is equal to the rise over the run, is equal to the mass over the volume, and that's equal to your density. Okay. So I've redrawn your graph right here. Once you have it graphed, once you have a slope, once you've calculated a density, let's just say you come up with a density of 1.5 grams per milliliter. And you're saying that the density of your clay is 1.5 grams per milliliter. You're not done yet. Because the second part of this project is for you to actually predict what it is. What is it? So what I want you to do is to go onto the internet, and I want you to find some values for the density of different types of clay and find out which value comes closest to what you have measured, right? And if you find a value on the internet for the density of clay that comes close to your value, then there's a good chance that this is actually that kind of clay, okay? A couple things I need to point out. You measured the volume by volume displacement, and you used a graduated cylinder that gave you the volume of milliliters. When you go on the internet, you're probably going to find density for clay written as grams per centimeter cubed. Don't let that bother you, because, very important, 1 milliliter is equal to 1 centimeter cubed. So even though the units look different, a milliliter is actually equal to a cubic centimeter. So you use the same numbers, okay? Let's just say you looked up on the internet and you found a value for Play-Doh, let's just say, as 1.62 grams per centimeter cubed. And of all the densities that you found for clay, that one was the closest. So you would write in your paragraph, I predict that my unknown substance was Play-Doh. That my unknown substance was Play-Doh. Because I found on the internet, and then you state your source, say, I don't know, the Artists Guild reported the density for Play-Doh as 1.62. And that came close to my value of 1.5. In fact, it was within so many percent. This is where I want you to calculate percent error. This was one of the other learning objectives that we had. So to calculate the percent error or the percent difference, that's equal to your experimental value, or what the value that you measured, minus the accepted or the theoretical value, divided by the theoretical value. Make sure that this is an absolute value. We don't want any negative signs in our answers. Then you multiply this times 100, and then you get your percent difference. And that tells me how close you were able to predict what that unknown substance was. Okay? So this is an overview of your project, trying to find out what is in the bag by measuring the physical properties of the mass and volume, determining the density, and matching that density with known values on the internet, and then telling me what your prediction is. Okay?